Can't stop, slow down. I want you, I want you. No cold, no rain. One kiss, no pain. Tell me again. I want you, I want you. You don't wanna talk, then you wanna talk, then you wanna tell me I'm wrong and to move along. Then you wander back in my heart like a bitter song. And we're never done, cause I need your love, I need your love. California, hallelujah. You and me gonna live for today, girl. I'm the luckiest man in the whole world. Stole my heart from California. All I know is I'm with you today, girl. I'm the luckiest man in the whole world. Lies you don't keep, her and I'll be. But you're so sweet, and I want you, I want you. You don't wanna talk, then you wanna talk, then you wanna tell me I'm wrong and to move along. Then you wanna back in my heart like a bitter song. And we're never done, cause I need your love. You don't wanna talk, then you wanna talk, then you wanna tell me I'm wrong and to move along. Then you wanna back in my heart like a bitter song. And we're never done, cause I need your love. You and me gonna live for today, girl. I'm the luckiest man in the world. Stole my heart from California. All I know is I'm with you today, girl. I'm the luckiest man in the whole world. Come on, come on, just love me for one night. Just love me for one night. California, hallelujah. You and me gonna live for today, girl. I'm the luckiest man in the whole world. Stole my heart from California. All I know is I'm with you today, girl. I'm the luckiest man in the whole world. California, hallelujah. I'm the back of my heart like a bitter song. And we're never done, cause I need your love, I need your love. Stole my heart from California. You're on the back of my heart like a bitter song. And we're never done, cause I need your love, I need your love.
I guess just about everybody's here. Okay, let me share a screen so you can see where you can go and what you should see today. Let's see here. Check and make sure this sounds good. Sounds good. All right, so in our Schoology page and materials, and then in Unit 5, I put a folder to help you just organize just for today, and then I'll take the stuff out of the folder, but this is just so you can find things easily today. In week of 12.1 to 12.4, there's a folder here that says Electronegativity materials for the 12.4 class. There's also this electronegativity and bond type homework. This is a practice for calculating values for types of bonds that I'll show you how to do today. This should also show up on your upcoming list on the right-hand side. But in the folder that says Electronegativity materials for the 12.4 class, there's an electronegativity table here. And what this is a periodic table of electronegativities. And you can just Google like an electronegativity periodic table or whatever, but this one's directly in the folder as a reference for you. And what the table shows is the element symbol, the atomic number, and then underneath it is the value for the electronegativity. Whenever we did periodic table trends, we looked at relative atomic size, relative atomic number, things like that. Oop, let me check. We got somebody else coming in. Participants. There we go. All right, now just about everybody's here. And one of the trends was that for electronegativity. And if you remember in that trend, fluorine, way up here in the upper right-hand corner, had a very high electronegativity of 4.0. And then down in the lower left-hand corner, francium has a very low electronegativity of 0.7. There's some other values down here for the lanthanides and actinides, but generally, as you go from the lower left-hand corner of the periodic table to the upper right-hand corner, the electronegativity increases. So for any individual column, as you go from like francium up through hydrogen, the value increases here from 0.7 up to 2.1. In the transition metals, it's a little bit goofy because it turns out the electronegativity actually goes down just slightly right here in the middle. But over toward the right, the electronegativity increases from 2.2 to 4.0. So generally, as you go up on the periodic table, the electronegativity increases. And also as you go to the right, the electronegativity increases. So for any individual row on the periodic table, like period 3, it goes from 0.9 to 1.2, 1.5, 1.8, 2.1, 2.53. So these numbers underneath the element symbol on this table is what I'm going to be referring to today in this class. Let me bring up just 1 second. I need to get that as a reference on another computer here so I can see it. And then what else is in there is there's a PowerPoint slide deck that says HC, that's honors chemistry, polar bonds, and electronegativity notes. And this is what I'm going to be showing you and referring to for like the next few minutes here. So we're going to go over these notes, and you always have them available right there. And then there's a worksheet that we're going to do together in class. I'm going to give you a few minutes, and then we'll check that. And then once you're able to figure out how to determine whether a bond is polar, nonpolar, or ionic, then the homework is like a self-grading homework that's in the updates. And you could do that today. As long as you get it done by Monday, you'll be good, because we're going to be doing a bunch of stuff related to electronegativity and bonding during next week. Hold on, just give me 1 second here. 5. All right, so you can just watch this, or you can follow along and whatnot. Let me check and see if that looks okay. Yep, that's good. I'll just leave it as like a full screen here. 17%. It's about to die. All right, so in chemical bonding, bonds occur either because atoms are attracted to each other as they become ions, or you can have bonding that takes place between a metal and a non-metal. That's another way to think of it. And whenever ionic bonds occur, there are electrons that are transferred from whichever atom becomes the cation to the atom that becomes the anion. And the bonds for in ionic bonds are very, very strong. There's a large difference in electrical charge between the anion and the cation. In covalent bonds, atoms share electrons, and it's usually between two nonmetals. They're usually P group elements in the upper right-hand corner of the periodic table. The electrons aren't transferred from one atom to the other. Instead, they're shared between atoms, and the bonds are not as strong. So it turns out that for ionic bonds in what forms salts and crystals, those bonds are incredibly strong. The atoms are held together very, very tightly. And it's partly because there's a large difference in electronegativity. So whenever you refer to like the periodic table with electronegativities, let me just switch back to this other one here. an instance of that is I don't know why this is being a little bit slow today. So like one example is carbon dioxide. Carbon dioxide is a gas that's in the air that we breathe. It's a gas that you exhale. Carbon dioxide is covalent, and for that carbon dioxide is covalent, there's not a large difference in electronegativity between the two atoms that make up carbon dioxide. There's carbon and there's oxygen. And carbon has an electronegativity of 2.5. Oxygen has an electronegativity of 3.5. So carbon and oxygen, the difference in electronegativity by subtracting 2.5 from 3.5 gives you just 1. Where on the other hand, sodium chloride, which I've used as an example a little bit, that's common table salt, has a very strong ionic bond. The chlorine has an electronegativity of 3, but sodium has an electronegativity of only 0.9. So the difference in electronegativity there is 2.1. The really big deal is what the difference in electronegativity values are, and I'll show you the criteria for that. Also within covalent bonds, some bonds are polar and some bonds are non-polar. And that has to do with how equally shared the electrons are between the two atoms. If electrons are more equally shared between two atoms in a covalent bond, then the bond is non-polar or closer to non-polar. If the electrons are shared very unevenly between the two atoms, then it turns out that the bond is very polar, and there's a separate criteria for that. So I'll show you how those criteria work and how the math turns out here in just a second. This is another way to see the classification of bonding. Anytime atoms form together to make molecules or compounds, either as ionic or covalent compounds, generically that joining of atoms is called a bond. And there are two kinds of bonds generally: ionic bonds, where electrons are transferred from one atom to the other, and then the resulting anion cation are attracted electrically. The other type of bond are covalent bonds. And in a covalent bond, the atoms share electrons, but that sharing may be unequal. If the bond sharing is, or if the electron sharing is more unequal, or if one of them happens to be hydrogen, which only has 2 valence electrons anyway, then the bond is polar. And if the sharing is very equal, then the bond is nonpolar. So in a way, there are 3 total types of electron transfer or sharing that happens in bonds. Bonds are either ionic, or they could be polar covalent, or could be non-polar covalent. And that the 2 things that could happen is either electrons are completely transferred from one atom to the other, and if electrons are transferred from one atom to the other, then it's closer to being an ionic bond. And if there's electrons that are shared, and the electronic sharing is more equal, then it's closer to being a non-polar covalent bond. Okay, so here are the here's the criteria that you use to determine whether or not a bond is non-polar covalent, polar covalent, or ionic. We look at that chart of electronegativities, and the electronegativity values range all the way from a low of 0.7 for like cesium and francium, all the way up to fluorine for in the upper right-hand corner of the table. So you have values as low as 0.7 and as high as 0.4. What determines whether a bond is, we already went over this, like electronegativity trends. What determines whether a bond is nonpolar, polar, or ionic is the difference in the value for the electronegativity for the individual atoms. So a way to see it is if you were to have a bond that exists, like maybe for a metal, maybe we have an alloy of nickel and copper, and the electronegativities are each 1.9. Well, that's a metallic bond, but if it were to be described as a covalent bond, it would be a non-polar covalent bond because the difference between 1.9 and 1.9 is 0. If instead you have like nitrogen oxide or nitrous oxides, which are formed in the combustion of gasoline and automobile engines, because there's always nitrogen and oxygen present. The difference in electronegativity is only 0.4. 3 and 3.4, the difference is 0.4. It's not very large. But for compounds that are ionic, which are usually formed between alkali metals and alkali earth metals, way over here on the left-hand side of the periodic table, with low electronegativity values, and with halogens or group 6 elements with very high electronegativities, that difference in electronegativity value is much greater. All right, so here are some specific examples. This is how you do it. Non-polar covalent bonds exist whenever the difference in electronegativity is typically between 0 and 0.4. And that's something you can write down. So non-polar covalent is if the electronegativity difference is between 0 and 0.4, generally. The air that you breathe is mostly composed of nitrogen. The air you're breathing right now is mostly nitrogen. There is oxygen, and that's the component of the air that is most essential for you to have to be able to breathe. Air also has carbon dioxide, water vapor, some other gases. But the majority of the volume of the air you're breathing right now is just nitrogen. But nitrogen doesn't exist as individual atoms. Instead, it's N2. There are 2 nitrogen atoms that are bonded together. And those bonds that exist between the 2 nitrogen atoms are non-polar covalent bonds. Whenever an atom is diatomic, that's whenever it's like 2 of the same atom bonded together. Because nitrogen has an electronegativity of 3, and if it's bonded to another nitrogen atom, also with an electronegativity of 3, then the difference between that is 0. If it's 2 atoms of the same element, the electronegativity difference is just simply 0. That's it. In the case of a bond between chlorine and bromine, when you look on the electronegativity chart, chlorine has an electronegativity of 3, bromine has an electronegativity of 2.8. You just simply subtract the values of electronegativity. 3 minus 2.8 is 0.2. And so values of 0 and 0.2, they fit well within the range of 0 and 0.4. So bonds between nitrogen atoms, bonds between chlorine and bromine, the difference in electronegativity is 0.2. And what that really means is that the electrons are shared fairly evenly between the individual atoms. Going up in difference in electronegativity are polar covalent bonds. In a polar covalent bond, the difference in electronegativity is typically in a range from about 0.5 to 1.7. So that's the thing you can write down. In polar covalent bonds, the electronegativity difference is between 0.5 and 1.7. So some examples of that, if you have a bond between oxygen and chlorine atoms, go back and look on that chart. So oxygen has an electronegativity of 3.5. Chlorine has a value of 3.0. You just subtract those values. 3.5 minus 3.0 is 0.5. You had a bond between chlorine and carbon. That difference is also 0.5. A bond between nitrogen and hydrogen. That difference in electronegativity is 0.9. And what we expect then is that the electrons that are shared between those individual pairs of electrons, the electrons are not shared as evenly as if the difference in electronegativity were to be smaller. And then the third criteria is that for ionic bonds, let's see, and we just don't have a separate one there. The third criteria is for ionic bonds, and in ionic bonds, the difference in electronegativity then is just greater than 1.7, or from about 1.8 on up. So this is the total thing that you just need to know, is that if the difference in electronegativity values on the electronegativity periodic table is between 0 and 0.4, it's nonpolar covalent. If the difference in electronegativity is between about 0.5 and 1.7, it's polar covalent. And if the difference in electronegativity is about 1.8 or greater, then the bond is ionic. Here's another way to see it. In the case where electrons are shared, this shows like sizes of electron clouds. In the case of valence electron clouds. If you have two atoms that are bonded together and the difference in electronegativity is zero or very close to zero, the electrons are very equally shared, and those purple globs illustrate the distribution of electrons for the bond that exists between the two atoms. And if it's non-polar covalent, the electrons are shared evenly, and there aren't very many extra electrons on one side of the atom or one side of the molecules compared to the other. As bonds become polar covalent, the difference in electronegativity becomes greater, and the electrons are shared more unevenly. And so those two orange glob, or the two purple globs in the middle of that chart, show that there's more electrons on the right-hand atom. That would be something that has a higher electronegativity than for the left-hand atom. The atom on the left has a lower electronegativity. It has a lower ability to attract electrons. That's ultimately what electronegativity is, the ability for an atom to attract electrons. In the case of ionic bonding, the electrons are completely transferred from one atom to the other. And I would say that in that example, the atom on the left would be probably hydrogen with only some 1s electrons, and the atom on the right would be a much larger atom that has a larger number of valence electrons. So maybe that is actually like, I don't know, hydrogen chloride gas, or maybe, yeah, or maybe it could be like lithium fluoride, or something like that. All right, let's see. The difference in electronegativity whenever the electrons are unequally shared creates what we call a dipole. Di means two, and then, pole means there's a separation, or two different ends. And the activity from yesterday with the polar bear thing with dipoles gave you kind of an introduction to that. In the case of a polar covalent bond, one end of the atom is more negative than the other. And in this little description here, if you have a bond between carbon and oxygen, the oxygen has a higher electronegativity than carbon does. So there's a greater concentration of electrons around the oxygen than there is around the carbon. And that is illustrated in your textbook. If you have a copy of your textbook, you can read about dipoles, or in all the materials that I'll provide for you. We use this symbol to mean partial. This symbol is the Greek letter delta, and the Greek letter delta, you might know the uppercase Greek letter delta, which is illustrated as a triangle. The Greek letter delta to mean difference in value, usually in mathematics, is the uppercase Greek letter delta, which is a big triangle. The lowercase Greek letter delta looks like that. It's sort of like the letter 8, if you write a letter 8 completely like that, but it isn't complete. Anyway, the delta with a little plus or delta with a little minus means partial positive or partial negative. So in the case of a carbon and oxygen bond, the end of the molecule, this is actually carbon monoxide gas. Carbon monoxide, the oxygen has a higher electronegativity. There's a greater concentration of electrons around the oxygen. So we say this end of the molecule has a partial negative charge. For the carbon, there's this lower electronegativity, so that end has a partial positive charge. Not to say that this end of the molecule is actually always positively charged, but there's a greater number of protons than electrons over here. It's the same with nitrogen and oxygen. Oxygen has a higher electronegativity, so this is the partial negative end of the molecule. For chlorine and fluorine, fluorine has a higher electronegativity, so that's the end that's more negative. Okay, so here's an example of how you figure out whether or not a bond is ionic or polar covalent or non-polar covalent. So here's an example. We're looking for a bond between silicon and sulfur. The difference in electronegativity, all you do is go find silicon, and silicon has an electronegativity of 1.8, and then sulfur has an electronegativity of 2.5. So all you'd really have to do is just write 2.5 minus 1.8. The electronegativity difference is 0.7, and the type of bond for electronegativity difference of 0.7 is polar covalent. For cesium and chlorine, you look on the chart, cesium's 0.7, chlorine is 3.0. So the difference between cesium and chlorine is 2.3, and 2.3 gets you an ionic bond. For silicon and phosphorus, silicon is 1.8, phosphorus is 2.1. The difference between 1.8 and 2.1 is 0.3, and 0.3 turns out to be non-polar covalent. So that's all you got to do to figure out what type of bond tends to form between those two individual atoms. So like as a summary, electronegativity scale tells us which atom has a greater polar attraction of electrons, and the greater the difference in electronegativity, the more likely it is to be ionic. So there's a practice here, but what I want you to do for just a few minutes here is go into the folder. So when you're in Unit 5, that's the current unit, there's this week, week of 12.1 to 12.4, and then I put the materials in a separate folder just for today so you can find it easily. Electronegativity material for the 12.4 class. And there's a practice here, the polarity and electronegativity worksheet. And maybe what you could do is, well, I'll put up the electronegativity periodic table too. Or if you happen to have your textbook, there's a table of electronegativities. Let's see, page, if you have your textbook on page 405, let's see, that's not a full table. Yeah, page 405 of the textbook has some electronegativity values, but it's not a complete chart. Oh, shoot. That doesn't show up. Oh, that's kind of messed up. Sorry about that. In the polarity and electronegativity worksheet that I'm showing you here, don't worry about question number 1, but you can go down as a practice down to, it's on the second page. I don't know why it got jumped down on the second page, but there's a chart there, and you can, ooh, this stylus keeps on going. There we go. So in the polarity and electronegativity worksheet, that's what it's titled at the top. It turns out it got jumped down to the second page, but take a few minutes here and look up the electronegativity values for each of the two atoms, calculate the difference just by subtracting them, use that criteria to determine if it's nonpolar, polar, or ionic. See, if you have a question, you can put it in the chat, or you can just turn on your mic. Lost the chat box. There it is. Let's see. 16. turning this in. Okay, this worksheet is just a practice for right now for in class, but the homework is on the right hand side for like your upcoming stuff, and it's in the folder for this week. There's an assignment that's the same sort of thing about it's like a multiple choice, figuring out if things are ionic, polar covalent, or non-polar covalent, and some stuff about individual individual bonds. So this worksheet you're not turning in. This is just practice for right now. And I have some solutions I can put up for that. Okay, so let me put the it's useful if you have more than one screen, or you can have one table on a like a laptop and one somewhere else. If you happen to have a printer, you can print something out. Let's see. I just took a picture, show you how I'm doing class today. That's what I'm looking at. Got like 2 computers, a screen, a tablet for writing on. That's how I'm doing it. Okay, let me turn this on. Publish. Okay, so in the folder for today, I just turned it on or published it. These are answers to that problem on that worksheet that I just asked you to give a try with. I don't know if that was the right amount of time. Usually when we're here in class, I can watch and see right and see what percent of you are finished and what percent of you aren't. I can't really tell that right now because all I'm looking at is black boxes with names on it. So anyway, those are values for electronegativity from the electronegativity periodic table. You write down the electronegativity values, and then you just subtract the numbers. That's all you got to do. And then you use the criteria. If the value for the electronegativity difference is between 0 and 0.4, it's nonpolar covalent. If it's between about 0.5 and 1.7, it's polar covalent. If it's greater than 1.7, then it's ionic. And just to tell you about these individual compounds, hydrogen and chlorine bond to form a gas called hydrogen chloride gas, and it's polar covalent. And then it turns out that when that gas is dissolved in water, because water is so polar, it actually pulls the hydrogen and chlorine apart and makes an acid called hydrochloric acid. It's also known as muriatic acid. And hydrochloric acid is the main acid that's in your stomach. That's what stomach acid is. Hydrogen and hydrogen is diatomic. That forms a bond to make hydrogen gas. And hydrogen gas has a low density. It's been used in the past. Well, it's a flammable gas, so it can be used as a fuel, but it was also used to fill dirigibles like the Hindenburg was filled with hydrogen instead of helium, which is much safer. Chlorine and chlorine bonds as diatomic to be chlorine gas. So whenever there are diatomic molecules like hydrogen and hydrogen, that's nonpolar covalent. Chlorine and chlorine, nonpolar covalent. You can always know that if it's two atoms of the same element that are bonded together, the difference in electronegativity has to be 0, so it's nonpolar covalent. Carbon and oxygen is a very common bond, maybe in carbon monoxide or carbon dioxide. The difference in electronegativity is 1.0, so it's polar covalent. Calcium and oxygen, well, that forms a salt called calcium oxide. And it turns out here at school, I buy calcium oxide. We mix calcium oxide with water and then drip it into our saltwater aquariums. And that gives calcium, that increases the calcium concentration in the water in order for coral to grow, because we grow live coral here at school, and the live coral has to build skeleton structures. It's also used by the fish and by clams and other kind of things that have to take up calcium. And calcium oxide is sold as a solid salt, and it's ionic. And then you could put it in the water and it'll dissolve. But the difference in electronegativity for calcium and oxygen is 2.5, so it's actually quite ionic. Aluminum and iron, well, if that was a bond that's covalent, the difference in electronegativity between aluminum and iron is 0.3. So that's nonpolar covalent. That's really all there is. It's not any more difficult than looking up the values for electronegativity, subtracting the electronegativity values, and that gets you the determination as to whether or not the bond is polar, nonpolar, or ionic. We'll use that information all through this course. Okay, so in the folder that said electronegativity materials for the 12-4 class, these are the notes that I went over with you, the polar bonds and electronegativity notes. This polarity and electronegativity worksheet was those examples that we just did. I'm actually going to move that down. And then the electronegativity answers, that thing I just showed you, Those are answers that go along with the practice problems that are in the polarity and electronegativity worksheet. The first thing at the top was the table that you can use as a reference. You can also just Google it. There's a bunch of different places you can find it online. There's just a million of them, not really a million. If you type like electronegativity periodic table, there'll be a whole bunch that come up. And they're all pretty much going to be the same with differences in electronegativity values. So like they just look different in color and whatnot, but they're all going to be pretty much the same values with the same reference numbers. Like here's one. And but I put that one right in that folder. Okay, so anyway, what you need to do between now and Monday, you can probably do it pretty quickly if you want to take some time now, but the next class starts pretty soon. On the right-hand side, there ought to be electronegativity and bond type homework. And when you click on that, it's a multiple choice thing about calculating electronegativity differences and determining what kind of bond forms between different atoms, just like we did. So you want to have a periodic table of electronegativities available, and a calculator, although it's not hard to just subtract those numbers. They're not like it's not hard math. And that'll help inform you whether or not the bonds are nonpolar, polar, or ionic. So anyway, that's all I have for you today. We used a good chunk of the period today. Hopefully that all made sense and went pretty well. If you need to, all these classes, I'm recording the Zooms. So this recording in a few minutes, I'll put it in the like the plan for the week. When you look at the plan for the week, right beside the date, it'll say Zoom recording, and you can look at that Zoom recording. So you don't have to do all the stuff on the right-hand side there. Yeah, well, the stuff on this bond type worksheet and the polar bonding with polar bears, these were items from like earlier in the week. Like this, I gave it to you on Tuesday, and this was from yesterday. So yeah, you need to do these if you haven't done them yet. And then the electronegativity and bond type homework, that's based upon this new stuff. Okay. If you have anything else, put it in the chat, or you can turn your mic on, ask a question. Otherwise, that's all I got for you today. Have a great weekend, and I'll see you on Monday.